Lisa Lippincott. I am here to talk about the shape of a program. But more generally, I'm here because I'm interested in this question. Why don't we routinely write down the reasoning behind our programs in a formal way and have computers check it? Because surely this would be valuable. We would like to have the reasoning behind our programs checked, but we don't generally do this. And it's a little hard to see the reason here, because we presumably know why our programs are supposed to work. We're very good at writing things down in formal ways. And we're very good about having computers check the things we write down formally. And yet, we don't do this, or we hardly ever do this. And my best answer to this question is this. The mathematical tools we use for proofs present a poor user interface for programming, and particularly for procedural programming. The math fights the programming, and it's hard to do both at once. I think the reason has something to do with this view of math. Many people understand math as describing timeless, universal truth. This is, I grew up with this idea of math, that math is the thing that is perfect and universal and timeless forever. And programming, on the other hand, is concerned with particular events and particular relations and exactly when things happen. Programming, and particularly procedural programming, in a word, is local. And this is really our watchword for good programming style. If it's not local, it's a problem for us. And our mathematics, the way we do proofs, isn't organized around making everything local. And I think that's why it fights us. So I think a big part of figuring out how to make mathematical tools that fit into our programs is finding the way to do the math entirely locally. Fortunately, there is a branch of mathematics that is all about locality. It's, I think, fair to say that it is the subject that tells us what local means. And that subject is topology. It's the basic mathematics of space and shape. So today, I'm going to dive into the topology of programs as best I understand them, and try to figure out a little bit about what local means in a program. So I invite you to consider all of the events, all of the relationships between events in the execution of your program, all at once. Consider all of them, and the way they are constrained to particular shapes, in the same way that the water flowing through this building is constrained by the plumbing. And we're going to look at that shape, the shape of all executions of a program at once. But first, a couple of warnings. I'm going to be talking about things you already know very well. The programming in this is not very hard because I wanted it to be very relatable. I'm talking about simple programming things, but perhaps with language you don't know. And in particular, a language you don't know, instead of writing the programs in C or C++, I'm writing them in a fantasy C++ with a few extensions that makes the proofs fit into the code. So I will try to explain those extensions lightly as we come to them, but if you want deeper explanations, you can look up my name on the internet. There are videos of me speaking at other conferences where I do go into the mechanics of those extensions in more detail. So with that said, let's talk about topology. Topology is about places. Places like a bunch of rooms in a conference center. But perhaps more important than these big blocks are the places in between, the liminal places, the places that are somewhat in a room and somewhat out of a room, the thresholds. Because the thresholds are how we get from one room to another. And this is really the picture of how topology works. We use thresholds to connect rooms together. In more detail, in topology, we have two kinds of sets. We have open sets, which are meaningful areas that don't include their edges. The edges are not in the open set, but closed sets are meaningful areas including their edges. So two kinds of meaningful sets. And I want to draw attention to that word, meaningful. This is a logician's spin on topology. It's not my personal spin. It's been around for a while. That topology tells us which sets have clear meanings. And it's that nature of knowing whether the edges are inside or outside that gives us the clarity. So I'm going to say today, sets that are neither open nor closed are not very interesting. They don't make meaningful distinctions. They make arbitrary distinctions. And that's the logician's view of topology. Conversely, when we control the topology, we control the meanings. So if we want to make something meaningless, we can change the topology, throw out those distinctions, and now those distinctions are meaningless. So to go with these, we have two operations. Closure, which is take a set, include all of the edges. Make it a little bigger so that it becomes closed and includes its edges. And the interior, make the set a little smaller so that it becomes open and doesn't include the edges. And these are the basic operations, a few axioms to make all of that work, and that's topology. If it sounds simple, that's because it's simple. It's one of the simplest areas of math, but these simple things build in interesting ways. The most important one for how I'm describing programs today is adjacency. Adjacency is sharing an edge. So we see that the closure of the purple room intersects the closure of the blue hallway. The purple room is adjacent to the blue hallway, and we can get from one to the other. The purple room is not adjacent to the orange room. But we can get from the purple room to the orange room by going through a few hallways. They're connected to each other. We form chains of adjacency, paths where at each point we're moving into adjacent areas, and we get to another room. That's connectedness. Now, I know a different conference where every lecture room is in a different building, totally disconnected from each other. So this is a distinction between that conference and this conference. This conference is connected, that conference is disconnected. So topological distinctions between conferences. But also programs. We can look in programs, we can use this idea of adjacency to form things together into sequences, a bunch of open sets, overlap it with edges that touch each other. We can be more complicated. We can have more than one, we can have more than two sets meet at a single edge. We can form branches and loops that way. But here we have a problem. If this were space, I can take a route like this. But I meant this to be a branch. That's not something you can do in branching in your code. And really the problem here comes from the fact that we're trying to model time in this picture, but we're using space. And we can take all sorts of crazy back and forth routes in space. Time isn't like space. Time is directional. I mean, it's famously directional. For all the points of the compass, there is only one direction, and time is its only measure. That's not me, that's Tom Stoppard. But it's a good line. So how can we describe directional space? And the answer, as I learned fairly recently, is to use two topologies. We use one topology for coming and one for going, one for entrances and one for exits. We make a bitopological space. And a bitopological space has four kinds of meaningful sets. They can be forward closed or forward open. They can be backward closed or backward open. But all four of these sorts of sets are meaningful in a bitopological space. You might notice these two on the sides seem a little familiar because these are what we could call half-open sets. These come up a lot in programming. They are fundamentally bitopological concept. There is no concept of half-open in a unitopological space. Half-open, half-closed is something that happens in a bitopological space. So, as programmers, we may be particularly interested in those. And the neat thing about a bitopological space is it changes our idea of adjacency. Adjacency becomes directional. Sets are adjacent if they are exit to entrance. So here, A precedes B because the forward closure of A intersects the backward closure of B. These sets are not adjacent in a bitopological sense. Sharing an entrance doesn't make you adjacent. Sharing an exit doesn't make you adjacent. To be adjacent, exit to entrance. And it's directional. A precedes B, but B does not precede A. Using that, of course, we can do the thing you expect. We put in directional edges instead of bidirectional unitopological edges. And we control the direction of flow through all of these pictures. And that gives us a more nuanced idea of connection. We have a directional idea of connection. Before is connection from A is before B because there's connection from A to B, but not from B to A. And we can have connection in both directions. There's connection from C to D and connection from D to C. They're along different paths, but they connect in both directions. And that's how we make loops. And I should point out here that this idea of connection is what topologists call a local property. It changes depending on the scope you're looking at. If we look in a smaller neighborhood, then D connects to C. D is before C, but C is no longer before D when we restrict our attention to this neighborhood. And sometimes we do that when we focus on the body of a loop. If we expand our neighborhood, we see more connections. Similarly, when we have a branch, we have two things that are clearly part of the same neighborhood. There's no easy way to separate this neighborhood into parts here. But these things, E and F, don't connect to each other in either direction. These are alternative possibilities. So no connection either way, alternative possibilities. And even if I expand them out, sharing entrances and exits this way, but not exit to entrance, E and F are not, neither before nor after each other. They're alternatives. So we have three ways to see connection here: before and after, alternatives, both before and after. These are all ideas of connection or disconnection in time. And I want to make that point, this one in the middle, alternatives. We don't always think of that as having to do with time, but that's what it is. Alternative possibilities are separated from each other bidirectionally in time. So that's perhaps important take-home number one from this talk, is alternative possibilities, bidirectional separation in time. So that's our basic flow control. I'm going to move on to a statement that I didn't give a lot of thought to when I started out programming, but has become more and more dear to my heart over time: the assertion. I like assertions because assertions are like statements of fact. They say, this thing is so. But assertions have a property that makes them better than facts. Assertions are tied locally into our program. They're experiments, not facts. And because they are experiments, there is so much less question about what an assertion means or what its scope is. If you want to find out what an assertion means, do the experiment. This is how you do it. It tells you what it means to test. There's none of this, what does it mean to say snow is white question here. Do the experiment. It comes with instructions. And I write an assertion this way, or I draw an assertion this way, is because successful assertions are repeatable and have no meaningful effect. If we test an assertion and it succeeds once, it should succeed over and over and over, no matter how many times we test it. And it should succeed in the same way. There should be no change to how it runs from one test to another. And I want to, once again, point out this word meaningful. Meaningful is how we bend the assertion into a circle. We alter our topology. Because, of course, if we test the assertion The world is different after we test the assertion. There is no action without consequence. That's the second law of thermodynamics, or which we have been so rudely reminded of by the specter bug this year. Every action has consequence. You can't go back to the same time. But what we can do is change our topology. We can say the differences between after the assertion and before the assertion must not be meaningful to us, because that's what it means to be an assertion. And that throwing those distinctions out of our topology lets us bend the assertion around into a circle, a sort of sideways time that doesn't count in the execution of our program. Stuff happens, just not stuff that counts. I know, by the way, that I am in good company here in Bristol, talking about sideways time, because the doctor has lectured here. So what does an assertion do if it just does nothing meaningful? Well, it tells us something. It describes this edge where it meets the rest of the program, where it begins and ends. And it describes its edge in dimensions of space and possibility. It's 5 feet high the door, 5 feet high the door, and 3 may walk abreast. And you can think of the assertion as the track that you run your army of dwarves around in order to test the shape of your doorway. And I think it's fairly obvious for people who have used assertions before how assertions describe possibilities. That is, if we test something Boolean in there, some conditions, some possibilities don't make it around the assertion, they're gone. And only the ones that go around are making the program correct. Space needs a funny kind of assertion. And I came to this realization by thinking about the things we needed to assert to actually show the preconditions we use fully in a program. And here are some examples of things that I think we need to assert, but we don't want people to branch on. We want to be able to say that something is readable or writable. We want to say that something is destructible, that its lifetime is not ended yet. We want to talk about memory that can be deallocated. And all of these on the left, things that we use as preconditions to core language ideas. Can we rethrow an exception? This last one is a funny thing with virtual base classes, messes that up. On the right, we have more library-like things that, again, we want to be able to speak of. We want to be able to assert. These are facts that we need. And in a certain sense, there could be experiments, but we don't ever want to assert the opposite. So we talk about dereferenceable iterators. We have a lot of functions that need dereferenceable iterators. No function needs a non-dereferenceable iterator. We talk about reachability. Reachability is interesting. That's a recursively enumerable condition, but it's not recursive. There is a test for reachability. We can do the loop. But there isn't a test for non-reachability, and that's why we can't make it a Boolean function. Resizability and reallocatability for a vector, these are preconditions that some functions require, and some functions in the standard explicitly disclaim. Some are allowed to reallocate. Some say, no, I don't need reallocatability. F-closable. F-closable is a property of an integer. 5, in some contexts at some times, 5 is an F-closable number. In some contexts and sometimes it's not. It's not like being prime. 5 is always prime, 4 is never prime. But F-closable is more of a local property. In some contexts, 5 is F-closable. Being in the past. Being in the past on your steady clock is a stable condition that you can assert over and over and over. Not being in the past is not a stable condition. That one can change on you. And come down to a favorite of mine, proper. This is what I've been using in my previous lectures to describe just the usual assertions associated with an L value of this CV qualified type. Kind of like a class invariant, but not a class invariant, an invariant, not even an invariant, it can change, but a property of an L value, being proper, being in the usual usable state. So given that most of these end with the same suffix, and I can make an edit, I can change these others to end in that same suffix. I call these capabilities. These all indicate things you can do because they can be preconditions to functions, and that's kind of how we know they're interesting, is that they are preconditions to functions. By the way, I like usable. I think usable is probably a better word than proper. So an object is usable if the usual assertions for its CV qualified type hold. So capabilities. And I'm not going to fully make the case at this point, but you might guess a lot of these have to do with what we think of, metaphorically perhaps, but what we think of as space in a program. Readable and writable is about memory space. Deallocatable is about space in the heap. F-closable is about space in the file system. Usable is about, there's a certain amount of space in that object that we are going to use. Even things like reachable, that's like, how big is that vector? Reachability. So this, I think, is how we connect to space in our assertions. We need these capability assertions. So that's assertions, describing their edge in dimensions of space and possibility. But there is one more aspect I want to point out about assertions, which is we need two kinds. It's not entirely obvious when programming with them that you need two kinds, because in terms of programming, the two kinds act alike. We need two logical kinds of assertions. We need claimed assertions and posited assertions in order to check the proofs in our programs, because we need to know where the proof is going to be. A claimed assertion is saying, by inspection of this area of the code, you should be able to figure out why this thing is true. So a claimed assertion, the proof is local. We like claimed assertions. Locality, we're in favor of locality. It's our watchword. And claimed assertions make our program fit together more strongly. Posited assertions are kind of the opposite. They are the assumptions we make. They are things that have to be true, but the reason for them being true may be far away, so we don't expect to find the proof locally in our program. In a certain sense, posited is the cast of assertions, where claimed is the type system. So with that, we can move on from assertions to another favored program construct. But first, I'm going to tell you a little story about how I used topology to get here today. When I was planning my trip to Bristol, I got out a map of the UK, and I plotted myself a route from where I landed in the UK to Bristol. But there was a problem. On my map of the UK, there was no Bristol. I mean, the word Bristol appeared on my map, but next to the word Bristol, there was just an empty circle. There was nothing in it. There was, in effect, a hole in my map where Bristol belonged. And that couldn't really get me to this hotel. So I got out a different map of Bristol. And I plotted a course to the places I wanted to visit while in Bristol. And I made sure that in this area in between where they overlap, which I will call the outskirts of Bristol, in the outskirts of Bristol, I made sure that I took the same course on both maps, because otherwise I could get very confused. And if I had used a bitopological map, my map would have been separated into ways into Bristol and ways out of Bristol. It wasn't. But if I had used a bitopological map, it would have been separated this way. And that describes my trip. Landing someplace far from Bristol, came to Bristol, visited places in Bristol, back out of Bristol, which I haven't done yet. If I wanted to make a map that showed my entire journey, what I would have to do is take my map of the UK and take my map of Bristol, line them up along the overlapping region in the outskirts of Bristol, and paste them together. And that's how topologists use maps. They paste them together to make bigger maps. More detailed maps sometimes, or bigger maps, more area. But we paste maps together in their overlapping regions using a process topologists call gluing. We paste the maps together to make bigger maps. And we call the map we make by pasting many maps together a manifold. And that brings me back to programming, because the way we make big programs is we take a lot of small subprograms and paste them together, making a manifold. This, by the way, is my favorite notation for the interface to a function. You know it's an interface because it has this statement, implementation, in the middle, where the implementation goes. And there's a prologue that comes before the implementation and an epilogue that comes after. The prologue tells you the ways into the implementation, and the epilogue tells you the ways out of the implementation. This, by the way, is in a certain sense not my idea. I think I may have learned it from Herb Sutter some 20-odd years ago, because this has been common practice for how we test that functions overriding a virtual functions satisfy a particular interface. For many years, we write an interface function that does the tests, that can make assertions in the prologue, make assertions in the epilogue, to make sure that the two sides fit, and then the implementation has to fit in between those sets of assertions. I want to point out one other thing about it. It is important that we can declare variables in the prologue that are used in the epilogue. That's why I like this written as a single block. That's why for 20-odd years we have been writing this as functions so that we can relate conditions that existed before the implementation to conditions that existed afterwards. This is an idea of function interface that takes change and time into account. So that's fairly straightforward, but what does it mean in terms of shape? Well, like assertions, we can look to the necessary properties of an interface to help us figure out what its shape must be. And interfaces aren't exactly repeatable, but they have something like repeatability, which is nestability. If you have written a proper interface to a function, you can nest it as many times as you want. If the claims in the prologue succeed once, they will succeed over and over again as deep as you want. And if the implementation manages to return, and the claims in the epilogue succeed once, they should also succeed over and over and over again as many times as you want, or at least as many times as the prologue was entered, because those variables that we need to save between one and the other are going to get destroyed in the epilogue. But if we can put one interface on a function, we can surely put 10 of the same interface nested on the function. So that's our clue. A nestable experiment in two parts is what we need for a function interface. And it's because we have these two parts because we are describing before and after. So an attempt at drawing this is this. We have a repeatable prologue and a repeatable epilogue. They look like assertions. And there's an implementation gap in between the prologue edge and the epilogue edge. That's where the implementation goes. That's the hole in the interface. The thing that when we call the function, we don't know what happens in there. We just know we're going to end, if it returns, we know we're going to end up in the epilogue. And I should say, this picture is not perfect. Because I didn't find a way to draw in those connections that you create by creating a variable in the prologue and referring to it in the epilogue. That's maybe a failure of my drawing skills. It's maybe a failure of my understanding. Maybe it's sort of a bypass between those two circles, or perhaps it's more of a donut. Topologists love donuts. I don't really know. I'm kind of hoping for the donut. But there is one more thing to know about. Like an assertion, an interface has two sides. From the caller's point of view, the assertions face this way. The caller has to prove the claims in the prologue, but the caller doesn't have to prove the claims in the epilogue. The caller takes the claims in the epilogue as posited. They're just given back to the caller, somebody else's problem. The implementation sees things the other way around. It takes the claims in the prologue as posited. It doesn't have to prove them, Caller's problem, but it does have to prove the claims in the epilogue. So when we paste them together, every claim has a proof. It's just when we divide into neighborhoods, when we divide our program into functions, sometimes we see a claim that's proved in a different function. And that's pretty much the logic of the possibilities here. The logic of the capabilities is similar. Certainly, the caller has to provide these capabilities, and the implementation has to provide these capabilities. But there's a little weirdness to it, so let's take a look at that. Here's a particular capability, deallocatable. Deallocatable is the capability that tells us how operator new connects to operator delete. In the epilogue of operator new, there is an assertion of deallocatability. It tells us this thing that I'm returning, deallocatable. In the prologue of operator delete, there's an assertion of deallocatability which says this thing that you're giving me has to be deallocatable. And when we use this, we keep track of the deallocatability, like a coin to spend at the arcade, that connects these two. In some connected, that's topology again. So let's look at this in practice. We have two separated statements, p equals new t, delete p. Don't write this, use unique pointer. But I'm going to write this to keep it simple. And if we look inside those statements, somewhere inside this first statement, one of the things it does, that's a hole inside the statement because this happens somewhere else. Operator new. There's a hole that operator new fits into. And somewhere inside delete p, there is a hole that operator delete fits into. And we know something about the interfaces to those two. Deallocatable is claimed in the epilogue of operator new. Deallocatable is claimed in the prologue of operator delete. And because of those claims of something that we don't know what it is, we don't know what deallocatability is. It means something. It means something to the heap. But it's atomic to us. On the outside, we don't know what deallocatability means. We just know it means something to some other part of the program. But these assertions connect the two. We know that there is some sort of tunnel through time from that event to this event. Something outside our neighborhood has to fit, has to be connected through that tunnel. So while we don't know what's in the tunnel, we are aware on the outside that the tunnel exists. There has to be a gap in our neighborhood that is the tunnel that fits something through it. And if we flip this around, if we look at the heap, here is a piece of the implementation of the heap. There's operator new and operator delete and deallocatability. Here, I draw it solid because the heap knows what deallocatability is. Operator new and operator deletes are friends of deallocatable. They have to know what that means. Or perhaps they know somebody who knows what it means or something, but really we're going to treat them as friends. So the heap is actually shaped this way. It's not a set of disconnected functions. It's a set of functions with connections between them. And when we paste our function to the heap, by calling new and delete, we have to leave room for these tunnels. There has to be something where we can put that to make them paste correctly. Otherwise, the shapes just don't fit together when we try to paste our program together. And that's really all there is to the simple use of capabilities and the conservation of capabilities. There can't be any leaks if there's always a tunnel for deallocatable to go through. A leak is you tried to paste something with no tunnel out onto something that had a tunnel out. And similarly, double deletes. You don't want to cross your deallocatables and have your program try to make one tunnel go to two different places when the underlying thing doesn't allow that. So really, the topology governs the resource conservation in a program. That's there in the shape. And the same thing is true for other sorts of capabilities. If we have a copy construction and an assignment here, we know that readable is a postcondition of copy initialization, and readable is a precondition readable on B is precondition of this assignment. So there's a tunnel that runs from that statement to that statement, tunnel through time. I should say, tunnels through time, running from the past into the future, again, seems very Gallifreyan. But really, they're fairly ordinary. We have an Earth word for a tunnel through time that runs from the past into the future. We call that a place. Anytime you're in a place, you are going from the past into the future. So, tunnel through time. Readable connects the copy initialization directly to the assignment, bypassing these other statements unless they also mention the readability. And I think your intuition at this point should be that somehow this connection carries the value of the variable. That somehow on the outside we know that value is running from A to B to C in this program. So, and this tunnel seems like the obvious place to carry the value. And I think that's true. And in particular, if we look at an experiment that shows us a Boolean variable definitely has distinct values, we can look at this a little more closely. What sort of experiment shows that a Boolean can have more than one value? Well, that experiment is, of course, an if statement. An if statement requires that this Boolean variable be readable. It's using that capability. Here we have interface to readability. You know it's interface to a capability because it says require implementation. Readability is a precondition to the if statement. But somehow that readability comes in two kinds. One kind that makes the if statement go left, and one kind that makes the if statement go right. This is a better picture of how an if statement works. Readable must be a tunnel with two bores, and it's possible for one bore to connect to a different place than the other. The true component of readable connects to one side of the if, and the false component connects to the other. Distinctions in value are multiple bores in the tunnel corresponding to readability. Separated how? Separated as alternative possibilities. Distinctions in value are, again, bidirectional separations in time. The same thing applies if we have a function that takes a const Boolean parameter here. Here, this function foo takes const bool reference b, and like any good function, it requires that its parameter be usable on the way in and on the way out. Usable for a const Boolean is just readable. A function like this separates into two components. It is as if there are two different functions with the same address, one for true and one for false, and there's no clear connection between how the two should operate. Really, if there is nothing that says that foo of true should do anything like what foo of false does. It's almost a selection between two different functions through the same interface because multiple bores in the tunnels. That breaks down a little bit, only a little bit, if this bool isn't const. If we have a writable variable, we need something that connects both ways. That is, if this bool that's not const is usable, that is, if it is readable and writable, because usable means something different if you're not const, then somehow we have to be able to get from the true component over to the false component during the execution of foo. And we have to be able to get from the false component over the true component during the execution of foo. So here we're a little bit more tangled. And the tangling has to do with writability. So what sort of shape does writability have that lets us do this crossing over? And the answer, I think, is that writable is adjacent to both bores of readability. That is, there's a sort of fork that happens, not a fork in possibility, but a fork in causality. Making a change like this is making a transition onto one track or the other of readability. This is a different sort of connection. This is a causal link between writability and readability. And again, we can write it here. Writability connects at the end to readability. This causal link is a kind of spatial relationship. This is unidirectional separation in space. You can go from writable to readable. You can't go from readable to writable. There's no causal connection from reading to writing. And we don't usually think of space we don't usually think of space as unidirectional, but here we are, causality, unidirectional connection in space. Bidirectional separation in space, that's what we think of as ordinary spatial separation. Using this, we can draw a little bit of the neighborhood of Boole, assignment, writable asserted in the epilogue to assignment, readable asserted in the epilogue to writability, which can connect in two pipes down to the if statement here. But I want to draw attention to this. We have a causal edge between writable and readable, crossing a temporal edge at the end of assignment. This is mathematically cool. This is the sign that this space is at least two-dimensional. This is why directed graphs aren't enough. Directed graphs are not multidimensional this way. Okay, that's pretty much what I have to say, but I will make one final apology for this. The boxes are a bit of a fib. Because really, if you look at the things I've drawn with boxes, there are parts inside, interfaces and so forth, edges between things defined by the interfaces. And when you get down to it, all of the action in a function happens in those holes where it calls other functions or basic operations. And that is, all of these neighborhoods are composed of nothing but edges. I mean, the edges can be in the interior of a larger thing, but there's nothing but edges. That's not something to be afraid of. The real numbers are the same way. But it continues. When we paste on to another function, we make our manifold. We're just filling in the holes, that foam that is our function, that has nothing but edges. We're filling in the holes with other pieces of foam. And we keep filling in other pieces of foam to make more detail, but it's still nothing but edges. It's edges all the way down, into the operating system, into the electronics, into the quantum mechanics. It's all interfaces. And our function fits into some caller, which fits into a caller, which fits into main, which fits into a hole in the runtime, which fits into a hole in the operating system, which fits into a hole in the computer, which fits into a hole in somebody's life. And it keeps going. It's edges all the way up. And I don't think this is a fact about programming. I think this is a fact about the human condition. Because we don't know the universe from the bottom up. And we don't know the universe from the top down. We can't. Because we don't start at the bottom, and we don't start at the top. We are born somewhere about the midriff. And we find our way outward from there. And the limits to our knowledge are interfaces to the things we don't know. So on that, thank you for listening. Are there any questions?
Am I on? Yes. I'm sure there are masses and masses of questions, but I think what we're going to have to do is close the session formally, and I'm sure that Lisa will be around, people who have those questions, to come and ask them and have, I suspect, very long chats, because I think it's going to take me ages just to sort that out in my head before I've got some real questions. So we'll close now, and could you thank Lisa for a really thought-provoking keynote?